CLion, a cross-platform IDE for C and C++. Download now.
So, welcome everyone. Today we are going to talk about asynchronous programming, coroutines, and the Tinycoro C++ 20 coroutine library. But before we start, something about me. So my name is Tamas Kovacs. I'm a software developer at Siemens. I'm also the creator and maintainer of the Tinycoro C++ 20 open source coroutine library. Generally, I'm passionate about C++. I enjoy reading and talking about it. But let's see the agenda. So as a quick overview, before we diving into C++ coroutines, it's useful to see how async programming is handled in other languages. So we are going to take a look into a little bit outside of C++, what's there regarding async programming. Then we are going to check the current status in C++ about coroutines. Then we will do some comparisons between different synchronization approaches. After that, we are going to dig a little bit deeper into the technical stuff. We are going to check what is a coroutine actually in C++, how we can imagine it, the functionality behind the scenes, what are the basics from Tinycoro, some comparison regarding traditional async programming and coroutine-based asynchronous programming. I'm going to share some common pitfalls with coroutines and a little bit of summary at the end. But now let's get started. So asynchronous programming, as we all know, isn't just a C++ topic. It's a fundamental concept in many modern programming languages like Python, Swift, C#, JavaScript. They have all built-in support for async functions, making the concurrency much more accessible for the developers and easier to use them. Why are those async functions so popular in those languages? Just a couple of reasons why. Of course, it's easy to use. The code is more maintainable and readable. There is no need for managing low-level thread and processes, so they eliminate the need for that. The better scalability, the automatic state management. So that unlike traditional callbacks, or thread-based concurrency, async functions preserve execution state, making the code more readable and easier to debug, and of course the energy efficiency, because async functions don't spin up unnecessary threads. They consume fewer CPU cycles, and they can lead to lower power consumption. So, but what's the status regarding coroutines in the standard C++? So while as I already said, many modern programming languages provide built-in abstraction for async functions, C++ take, of course, a different approach with coroutines. So we have also the keywords co-await, co-yield, and co-return, but those are not async functions yet, just coroutines. Coroutine is basically in C++ just a plain language feature with minimal standard library support. Yes, they are low level and flexible, but really hard to master. And if you would like to use coroutines in your code base, you have to write a lot of boilerplate code for that. So it's not so trivial to how to use them. But can we use coroutines to simplify asynchronous programming? Now let's see. But before we dive into this topic, we will do some comparisons between synchronous and asynchronous programming in C++. Just to recap, synchronous programming, there is nothing very special there. The benefits we all know, the top to bottom approach. So you are writing your code, the function basically from top to the bottom, and will be executed line by line. Therefore, the code became structured, and the program flow is easy. It's easy to read. The object lifetime management is also simple. There is no need for resource synchronization. So if you have some shared resources, you don't have shared resources at all because we are using only one CPU, so there is no need for mutex and stuff like that. Easier to debug, the deterministic behavior, and of course we all know that we have some CPU-bound tasks. So there are some algorithms which can only run on one CPU. So there is for sure the need for synchronous programming. But if you only use synchronous programming, of course, you are left a lot of performance on the table. And let's see just a couple of drawbacks there. Increased latency for IO-bound tasks. You can imagine if you have an application and you have to do some heavy calculations in the background, your UI can be frozen and the user cannot interact with the application. The limited scalability. You can do there some task management with prioritized level and stuff like that. They won't save you in the long term. And of course, as already the pure utilization of multiple processors. So you are left a lot of performance on the table if you write just synchronous code. But let's see what about traditional asynchronous programming. The first benefit, of course, the performance. So you can optimize your code for modern multi-core CPUs. You can utilize all the cores there on your machine, which is great. Scalability for high concurrency applications. This is also cool. And the one of the biggest benefit is the mature ecosystem. So if you run into some trouble, then you are going to find a lot of literature out there on the internet. So Stack Overflow and stuff like that, and they can most likely can help you with your issues. But what are the drawbacks? So as a traditional asynchronous programming, you can find yourself easily if you are working with completion callbacks, for example, in a nested callback hell. You have to do the manual resource synchronization. So you have to unlock shared resources. Therefore, the program flow can become unstructured and really, really complex. This leads to difficult object lifetime management and the potential threat salvation. So if you have some threats and you are waiting on some conditional variable in your application, this thread is basically blocked and cannot do anything, just waiting in your application. Therefore, the context switching overhead is bigger, and the error handling can become really, really complex. I mean that especially the exceptions handling. But what about the coroutine with asynchronous programming? First of all, let's see some of the benefits. Efficient for multi-core CPUs. This is basically pretty much the same as what we already saw by the traditional asynchronous programming. So you can use all the cores, CPUs, everything is there, which is cool. Non-blocking approach. This is an important one because that makes possible that on the suspension point on the coroutine, the underlying thread can be released, and the thread can do some other work, some other task in your application. So you are not blocking them, and therefore the context switching overhead is minimal. The top to bottom structure in your code, thanks to co-wait keyword, for example. So you are writing your code, which from the outside looks as synchronous code, but basically at the background we run asynchronously. Therefore, the program flow is easier to follow, at least as a traditional async methods. Simplified object lifetime management. The reason is behind the simplified object lifetime management is that coroutines are preserved in the execution state. So after resumption, the execution state is basically the same as it was before. there is no need for nested callbacks anymore. So every completion callback can be turned into the awaitable, which is cool, which you can co-await them anywhere in your code. Therefore, it's easier to maintain, and most of the time, as the code that you are writing with coroutines is also less. We are going to see some examples later on this presentation. And the improved error handling. Coroutines are supporting implicitly exception handling, and this is really cool and can be handy in some cases. So what are the drawbacks in the coroutine, this async programming? It still requires explicit synchronization, so you have to use mutexes, semaphores, and you have to lock the shared resources, but not as quite often as you would do this in traditional async programming. You are going to see them later if you start reusing the coroutines. The potential performance loss through the heap allocation. So most of the time, coroutines are allocated on the heap, although compilers are allowed to have to use them on the stack, to make them on the stack, not on the heap. But most of the time, this will not happen. So they can allocate. Probably they could allocate coroutines on the stack, but most of the time this will not happen. The debugging is not as easy, and of course the learning curve. So the coroutines-based asynchronous programming in C++ has not as big literature as the traditional async programming. So there is still the developers need still time to get used to it, get used to those 3 keywords, and they will take a little bit time still. So, but what is a coroutine in C++? Unfortunately, no one can be told what C++ coroutines are. You have to see it for yourself. A small first step. Let's see. A coroutine is basically nothing very special, just a generalization of a function with 3 key differences: that they can suspend and resume execution, can switch between different threads, and can be destroyed before completion. Now I'm going to show you guys some examples, some drawings, how a simple function call first look like. So as you can see there is a caller which calls the function. This is a simple function, not a coroutine. The function finishes with his execution, returning the control flow back to the caller, and the caller can exit from this context. And basically, this is a simple, easy program flow. But what about the coroutine? The coroutine looks a little bit different. So with coroutine, we can suspend the coroutine. In our case, there is one suspension point in this coroutine. So the caller starts the coroutine. The coroutine reaches his suspension point. In our case, this is in the co-await keyword. Happens here. After suspend, the coroutine gives back the control flow to the caller. The caller resumes later to resume the coroutine. The coroutine finishes with his calculations, returning back to the control flow to the caller, and the caller exits from his context. So in our case, that was just for a suspension point, and the coroutine can be suspended in those suspension points. But what about coroutines and threads? In our example, we have 2 threads, thread 1 and thread 2. Thread 1 starts the coroutine. Coroutine reaches his suspension point. It's got suspended, giving back the control flow to thread 1, and then comes thread 2 in picture and decides to resume the coroutine from its suspension point. Finishing the coroutine, return back to the thread 2 caller, and thread 2 can exit from this context. So the thing is behind that the coroutine can be resumed from different threads, and this can give you an idea how can become coroutine an async function now. But what about coroutine and the structure? So this destruction with coroutines can be made even from different threads. So as in our example, you can see the thread 1 starts the coroutine, same thing, coroutine reaches its suspension point, giving back the control flow to thread 1, and thread 1 can continue with its execution, and then comes thread 2 in picture and decides to destroy the coroutine. So one important thing to mention here, that the coroutine can only be destroyed in a suspended state. So if the coroutine is running and thread 2 try to destroy a running coroutine, this is undefined behavior. Please don't do that. So this can be only destroyed in a suspended state. And this destroy is basically a safe cleanup, because every object which is created on the coroutine frame here, cuts will be the destructors will be called guaranteed. So, and this is basically that code. This here is never executed, but everything above that is going to be destroyed properly. You can imagine this pretty simple things happening if you are throwing an exception for your function. The destructors also will be guaranteed call. This is basically the same if you are destroying a coroutine. So let's see a little bit overview of the Tinycoro C++ library, what it's offering for you, and what we can do with the library. First, let's see how a simple task and simple coroutine task looks like. So as you can see, this is here a simple coroutine. We are using the coroutine keyword. If you use one of the 3 keywords in your function, the function became a coroutine. And as you can see, our return value is not just the usual int32 type, but a Tinycoro task, which is wrapping the integer as a return value. Every task in Tinycoro is a lazy task. That means if we are creating the task will not start it yet until we co-await the task. So in our case, in line 6, we are creating the task in which we are invoking the foo coroutine is creating the task for us, and the task is co-awaited at the same time, and we are getting back our result 42. But what happens here? What happens here? We have basically the same structure. We have a coroutine which writes something on the standard output, hello. And here in this small program creates a coroutine task, invokes the coroutine, which creates a coroutine task. We are writing word, and after that we are co-awaiting our foo task. Therefore, the output is not hello world as you would expect from this example, but word hello, because in line 8 we are just creating the task but not invoking yet, not executing yet. We are co-awaiting them and executing them in line 10. That's why word hello is the output of this small program. But what about dealing with multiple tasks? What we have here is basically already async functions now, because we are using the scheduler. The scheduler is intended to run coroutine task, Tinycoro task asynchronously. So in our example, we have, this is our basic coroutine function, which reads a file from somewhere, from file path, and giving back the content of the file as a standard string, in returning in a file data as a standard string. But we have here in our foo coroutine that we are using the Tinycoro sync await helper function, which gets as the first parameter the scheduler, and after that it's coroutine function. These 3 coroutine functions are going to read file 1, file 2, and file 3 asynchronously at the same time. We are saving that here a lot of time with that. So, and returning back the data 1, 2, and 3 as a result. So in this example, foo task and read file task could use the same scheduler to run, so they can share all threads. And when foo waits for the read task, who will release the actual thread and can be used by other threads, like read file in our case. So despite the fact that schedulers uses only 3 threads, for example. So this is pretty cool. But let's move on. What if I want to cancel my tasks? So Tinycoro supports cancellation, task cancellation for sure. In this small example, we are going to use the Tinycoro any-of helper function, which gets the scheduler, and 2 coroutine functions, coroutine tasks. One is the consumer, which is basically waiting for an auto event, the auto reset event, called it, and wraps it in a cancelable object, in Tinycoro cancelable object that makes basically almost all available in Tinycoro cancelable. So if you have some event, then you can cancel them. And we have the return immediately coroutine function, which as his name mentions already, returns immediately. So in any of, in this helper function, the following will happen. If one of the tasks are finished, are done, they will automatically stop and cancel the other task. In our case, of course, we are waiting for this event. Nobody triggers this event, so this event wait would wait here forever. But after we are returning immediately in this function, invokes the cancellation process from consumer. They will be cancelled, consumer will be cancelled, and we can continue with this with the execution. This pattern turns out it is really helpful if you have, for example, some timeouts. So you start some coroutines, some async task, and you are collecting a timeout at the end. For example, just should run for 5 or 10 seconds, for example, and after 5 or 10 seconds, every other task will be cancelled. So this turned out in practice could be really useful to have some timeouts in your code easily. So can we turn traditional async completion callbacks into coroutines? I prepared an example for that, and let's see how can we deal with those problems. As we already know, we have completion callbacks. We have third-party APIs which has a lot of which could have a lot of completion callbacks which can be called in asynchronously, for example. In our case, we have one of these. I prepared one function, one simple function for that async download. The first parameter is just some URL, and the second parameter is the completion callback, which will be called if we are downloaded some data from the given URL. Let's see how can we solve this problem with traditional C++. So there is a simple download function. What we want to download is there. As you can see in line 7, we are invoking the async download, the third-party API. This is basically the URL, and this one here is the completion callback. What's happening in the completion callback, if you are getting the data, we are validating them, and this validation can throw an exception, for example. And if there was some exception, we are saving the exception and notifying the latch. If there was no exception, we just save the data in our result buffer and also notifying the latch. As you can see, we are waiting on line 20 in the latch. This is important. This is a thread blocking wait. So this thread, the underlying thread, is blocked and should wait here until somebody notifying the latch. After it is notified, we are checking if there was some exception. If there was exception, we are rethrowing the exception. Otherwise, just return the result. So this is already pretty complex logic, but it's for such a simple task. But let's see how can we deal it with in a coroutine based world. As you can see, the first what you can realize that the code is so much less and so much easier to read. So what we have here, we are using the Tinycoro async callback await a helper object, which is intended and designed to turn every completion callback into an awaitable. So you can await them pretty easy. The first, they need two callbacks. First is a lambda function, and the second one is basically the real completion callback. What's happening here in the completion callback, as you can see, we are validating the data and resulting the data if it was okay. As you can see, there is no exception handling there. What's happening here? What is if validate may throw an exception? Answer is nothing very special. The exception is handled implicitly through the async callback awaiter and the coroutine based support for exceptions. So the exception will be propagated to the caller, to our download with coroutine. So if you want, you can here write, for example, a try catch block, and you can catch the exception or just let them fly higher in the stack. It depends on your needs. But what we have here, so the second callback is basically the completion callback, and the first one, this is an interesting one. This gets a wrapped callback, and we are passing this wrapped callback to our third-party API through our async download function. Why is that needed? Because somebody has to notify our coroutine for resumption, and this wrap callback, the wrap callback is intended to notify the coroutine if the completion callback is finished. So therefore is the need for this wrap callback. But how much easier is to write concurrent code now? I have another example for that. So the async binary tree. What we want to iterate over a binary tree asynchronously, and we are going to use 2 threads for them. And as a result, we will sum up all the values that we find in the nodes. So first, let's take a look how a node should look. The node look like. As a node, pretty trivial stuff. There's nothing special there. We have a value inside the node and the left and the right child. So basically, pretty simple, standard binary tree. Wow, this is how it should how it looks like with the traditional C++ tools. As you can see, I had a hard time to fit it on one slide. Sorry for that. The important thing here, we are using 2 threads, thread 1 and thread 2. This is basically the worker, the lambda function, which we are going to pass for the threads. What's happening inside? We have a queue which holds the nodes, and we are start waiting on this queue with the conditional variable. After something was arrived in the queue, we are popping out the value from the queue, checking if there's a left or right child from the value, and pushing back to the queue. And of course, we are summing up the value that we have found in the node. Other code is just some boilerplate code to make cancellation possible and to make sure that that we are pushing the first node into the first node into the queue, and at the end we are returning the summed up value. So this is a lot of code for this small task. But let's see how can we solve this task with coroutine based code. As you can see, the code is so much less. So what we have here, we have a scheduler. We initialize the scheduler, initialize with 2 threads inside. And this is basically our coroutine function, which is going to get a node as a parameter. We are checking if the node is a valid one, it's not a null pointer or something like that. And if there is something in the node, we are recursively calling the coroutine with the left and the right side, and we are just co-evaluating for these results. So we are using, as you can see, the sync await helper function, which gets a scheduler as the first parameter, and after the left and the right side from the node. And after they are returned with the value, we are summing up with the current node left and right value and returning them back to the caller. So those two programs doing the same output, but this is so much more readable if you're using coroutines for this task. So in this example, of course, I only wanted to demonstrate how much simpler it can be writing concurrent code with coroutines. There are a lot of benefits. It's much less code, easier to maintain and read, code quality, etc. But in this special example, the coroutine version is about 3 to 4 times slower. This is probably now 2 or 3 times slower because I made some improvements, the performance improvements implemented, for example, a log-free queue inside the scheduler and stuff like that. But it's still slower. Although the coroutine version is slower, but this is only true for the traversal part. So we are traversal. If you are traversal in the binary tree, so when you have some heavy calculation in each and every node, the performance difference can be significantly less. And I mean there, if you do here some heavy calculations, of course we are now just summing up some values, some integers, but if you do here some heavy calculation, each and every node, the performance difference is significantly less between those two versions, implementations. So let's move on. Are coroutines the silver bullet for everything? Probably not. Object lifetime is important. We have to do it with care. I prepared a small example. So as you can see, we have a coroutine function here because we are co-returning, and pretty standard stuff. A const standard string reference as a parameter. In our case, we are creating the coroutine task in line 7 in order to invoke the full coroutine function, which creates our coroutine task. But as you can see, we are creating them with a temporary hello string, which gets immediately destroyed after line 7. And if we try to co-evaluate this task, this string is basically already destroyed, and this is an undefined behavior. Another example. This is basically almost the same as the previous one. So we have a const string reference as a parameter, but we are now co-evaluating. We are creating the task and co-evaluating at the same time. And the question is it safe? And I'm going to answer that, yes, this is safe, because although this is a temporary string, but it's going to outlive the coroutine execution of the coroutine task. So this is not an issue. The issue was, for example, in the example before, if you are creating the task with temporary and trying to co-evaluate later. But my general recommendation would be, anyway, if you can, please try to avoid the pointer and reference semantic in your function, in the coroutine function parameters, and copy the value if you can. Because if you are copying the value, you are always on the safe side. So in our case, we are creating the full coroutine task with the full coroutine function. Although this is a temporary, but we are copying them onto the coroutine frame, and therefore we can safely invoke them and co-evaluate this task later. This is fine. This is not an undefined behavior. So if you can, just try to avoid the pointer and reference semantic. But what about struct and classes? So in this example, my class has a coroutine function member, which is returning just the value of this class. So as an example, we can create we are creating my class here temporary, invoking his get value member function, which gives us the task, and we are trying to correlate them. Of course, as you can already see from this example, this is undefined behavior because my task is a temporary task and will be destroyed after line 10. And in line 13, if we try to correlate this task, the underlying my class is already gone. This is basically the same. My class is everything the same. We are returning the value, get value, but the only difference is, although this is a temporary my class here, and we are invoking his get value function, but at the same time we are also correlating but the return task. So my class will automatically outlive the execution of our coroutine. Therefore, this is a safe operation. But what about lambda functions? Lambda function can become also coroutines if you are using one of the three keywords on the coroutine. In your lambda function, we are using now co-return, but of course, for lambda functions, you have to explicitly then define what are the return value of your coroutine. So what we have here is an immediately invoke lambda function, as you can see there, which creates a task, and we are trying to correlate this task later in our code base. This is undefined behavior, and the reason why is that we are using the lambda capture, because if you are using the lambda capture, your lambda became a lambda object, and object has a lifetime, and this lifetime will end after line 5 and will be destroyed, and our task will not able to reach the underlying coroutine anymore, and this is undefined behavior. But how to make it safe, at least a little bit safer? So my general recommendation is the following in this case: avoid the use of the lambda capture if you can. Use instead the parameter list. So in our case, we have still the immediately invoke lambda function. So we are creating the lambda function and invoking them, which gives us our Tinycoro task here. But the important difference is that our capture is now empty, and we are passing the value as a parameter. And therefore, this lambda function is not an object anymore, so they have no lifetime. So this is just like a free function, which has one unique address in your entire program, and you can reach them anytime, anywhere from your program. So this is a safe operation, although we are immediately invoking it, and the task, because the task can reach, if you are correlating the task, the task can reach the underlying coroutine, because the coroutine is still there, because it's just like a free function. But there is another solution for this coroutines and lambda problem, that you can use the Tinycoro make bound helper function, which creates for you a special task, which makes sticky the task object and the underlying coroutine. So the underlying coroutine will be copied into your task object, and therefore you can move your task everywhere in your code, and you can correlate them later. You can also use your lambda function with the capture list. It's not an issue anymore. You have to be aware that the value still needs to exist, but this is pretty trivial stuff anyway in lambda functions. But the task is always going to have access to the underlying lambda function. So just a quick summary about Tinycoro. But the benefits from Tinycoro is, of course, this is a header-only library. It's cross-platform, so Linux, Windows, Mac is running everywhere. It's MIT license, so you don't have to worry about OSS clearing. There are no dependencies, no additional dependencies. It's easy to integrate. You have to just copy the include folder into your project, setting up the C++20 compiler, and it's going to be, you are going to be able to use them and play a little bit with coroutines. It's open source, and you can focus on your project, on your business logic, really on your coroutine. You can play around with them easily and learn and you learn and get to use these 3 new keywords in C++: co, return, co yield, and co await. Compilers: GCC, CLang, MSVC. From GCC, I think it's from GCC 11 to 14 is running on the pipeline. From CLang from 14 to 19, and MSVC, I believe it's 22, I think, this is one which is running on the pipeline. We have around 1,000 unit tests, so it's heavily tested also. And yeah, basically that's it. So use only as prescribed, just like through medication. Use coroutines wisely, please, and have fun with them. Thanks for sticking with me until the end, and I hope this can give you a better understanding of coroutines and how to use them safely. Coroutines can make, of course, asynchronous programming much cleaner, but as we saw, the object lifetime management is important, and we have to do it with care. So if you are feeling motivated or interested in contribution, I love to hear from you guys. You can reach me out on any platform and join to our Discord channel. You can check out the library on the GitHub, and there are a lot of examples there. Have fun and see you next time. Bye.